Just a quick reminder here that we have three colligative properties that we focus in on: boiling point elevation, freezing point depression, and vapor pressure reduction. Furthermore, we talked about in class the other day that a colligative property is one that depends on the concentration of the solute particles, but not on the nature of the solute itself. And that's an important thing. Again, you've already written that down in your notes from our class on, what was it, Tuesday. We didn't actually finish things up in our class on Tuesday, so I'm going to continue to talk about tomorrow, not in this screencast, but tomorrow, about the concept of vapor pressure reduction and how that relates to boiling point. But for now, I'm going to actually move us on to word problems that you would encounter when it comes to colligative properties. And the kinds of word problems that you would encounter are all about the effect that the concentration of a particular solute has on the boiling point or the freezing point of a solution. So let's focus on just the concept of how the concentration of a solute affects the boiling point. And don't forget that with boiling point elevation, whenever you add a solute and compare the solution to the pure substance or the solvent all by itself, you're going to have an increase in the temperature required to boil that particular substance. So the key element is that we're going to have an equation that we use to determine that change in the boiling point. So change, delta, is also known for a symbol for change, and then temperature is what we're looking at, but we want to look specifically at the boiling point. So it's T sub B for the boiling point, which is going to be a temperature in Celsius. And we can determine that change by multiplying the molality, and this is important because we want to make sure that we do something that's not going to be affected by temperature, right? And molality deals with kilograms as the denominator instead of liters as the denominator, and so it will not be affected by temperature. And it's going to be that, what is that all about? It's going to be the molality times a constant for that particular solvent. Okay, so we call that constant capital K sub B for the boiling point of that solvent. And in most cases, we're going to be using water as our solvent. So you should know that water is going to have a K sub B, boy, my stylus is not working very well, of 0.51, and then the important part is what are the units associated with the KB, and the units are degrees C per molal. Oh my God, that's not an M. That was some funky thing that I've never seen before. Okay, so those units here are important for you to keep into your brain because obviously if you're going to be multiplying this KB by molality, then the thing that you're going to be left with is the degrees C, and that's going to be the change in the temperature, boiling point temperature from the solvent by itself. So let's see how this works with a particular problem. Okay, so here is the problem. What is the boiling point elevation when 12 grams of iodine is dissolved in 100 grams of carbon tetrachloride, or CCl4? Hold on, my daughter just texted me. I have to text her back. Okay, so this is how we would approach this problem. The first thing is we're going to determine the number of moles of the solute that we have here. And since I have 12.0 grams of iodine, and iodine is a Hänkelbrief, so it's an I2, and my equivalency is 1 mole of iodine, and I look it up on the periodic table, and I figure out that 253.81 grams of iodine is equivalent to 1 mole. And when I crank this out, we have this as my number of moles of I2. And then I want to determine the molality of the solution. And to determine the molality of the solution, I have to take the number of moles of the solute that I've worked with, and that's the number of moles of I2, and I'm going to put that over the number of kilograms of carbon tetrachloride, which is the solvent. And if you have 100 grams of carbon tetrachloride, that's equivalent to 0.100 kilograms. It's very important that you convert that of carbon tetrachloride. And when you put that together, it works out to be 0.473 as my molality. Now, obviously, we aren't done because what I want here is not the molality. I want to know what my boiling point elevation is for this. So, let me copy this whole thing and move to another page. Okay, so then I'm going to use that equation that I just gave you moments ago, and that's going to be the, oops, hold on, I got to go back to delta T sub B is going to equal the constant for that particular solvent times the molality of the solution that you're working with. And so we know that the constant, since I gave that to you in the problem, with 5.02 degrees C per molal, and now we know the molality. When you put that into your calculator, you get 2.37 degrees C, and so that's going to be the boiling point elevation. Now, I have no idea what the boiling point for carbon tetrachloride is, but let's imagine that it's 40 degrees C. So if it were 40 degrees C, then you'd need to add 2.37 degrees to that 40 degrees C to get the new boiling point. Keep in mind that this here only gives you the change in the boiling point. It doesn't give you the new boiling point. All right, so let's take a look at another problem, which is going to use the same process, but I sort of go about it from a different standpoint. All right, so you shouldn't be too surprised that we need to first figure out what the molality of this solution is going to be. We know that the temperature, the change in temperature is going to be 8.57 degrees C, so that's going to be our answer. And again, we're going to be using this same thing right here. Let me go ahead and copy this right there. All right, so if we're going to use that same equation there, we know what the KB is because it was given to us right here. So I'm going to go ahead and put the 2.67 degrees C per molal, right? And we're going to multiply that by the molality. Now, of course, that's what we're looking for. So when I throw this into my calculator by solving for molality, that's going to equal, and I get 3.21 for my new molality, or not my new, for my molality. And don't forget here that molality is the number of moles over the number of kilograms. So it would be equivalent to writing 3.21 moles of the what is this stuff? C8H10O2 over 1 kilogram of benzene, right? And what we want to do is figure out how many grams of this C8H10 that we need to put in there if we have 98.7 grams of benzene. All right, so I don't have a full kilogram of benzene, I have a much smaller portion of benzene. So that means I take my 98.7 grams, and I first need to convert that into the number of kilograms. And by the way, just so you don't screw it up, you should always do this out, as much of a pain as it is. So if you know that 1,000 grams is equivalent to 1 kilogram, and you should know that if you don't, then that's what you need to use as your equivalency when you're doing this. So you essentially are going to simply divide 98.7 by 1,000, but if you do the equivalency, you won't mess it up. And when you do this, it's 0.0987 kilograms. So I take my 0.0987 kilograms of benzene, and I'm going to multiply that by the equivalency that I have right up here. So that's 3.21 moles of C8H10O2 divided by 1 full kilogram. my benzene. And when I chuck that into my calculator, I then get 0.317 moles of C8H10O2. And I'm not done yet because remember, the original question asks how many grams of this stuff do I need to have? And so that brings us then to do a simple mole conversion. So I'm going to take this information right here, 0.317 moles of C8H10O2. Oops, that's not a 2. Geez, that's still not a 2. And to do this mole conversion, whoops, I want to have 1 mole of C8H10O2 on my denominator, and the molar mass of C8H10O2 is 138.164 grams. And when I chuck this into my calculator, I get an answer of 43.8 grams of C8H10O2. Now don't forget, let's go back to our original problem here. It asked how many grams of the styrene glycol must I dissolve in 98.7 grams of benzene to raise the boiling point by 8.57 degrees C. Well, that's exactly the answer that I have right here. I put that into my 98.7 grams of benzene, and when I try to boil the benzene, it won't boil until I get 8.57 degrees above benzene's normal boiling point. All right, so there you go. Tomorrow in class, like I said, we're going to go backwards a little and talk a little bit about how boiling point elevation is impacted by vapor pressure reduction. And we're also going to be doing some word problems in class as well. Bye.